Okay, last time then, we were looking at uniform convergence, and we talked about function balls, and then we looked at this example to start with, the functions x to the n, and we first defined them on the closed interval 0, 1, and we saw that they converged pointwise to this funny discontinuous function in orange, which went along the axis until it reached x equals 1, when it suddenly jumped up and had a discontinuity. So we had pointwise convergence of this sequence, but not uniform convergence. And then I quickly tried to show you a second example defined on the interval 0 to half. And as always happens if you try and do things in a hurry, there was a slip in what I wrote down, which I'll show you now. So started off okay. I did note that x to the n was between 0 and 1 over 2 to the n. And then I said let epsilon greater than 0, and I wanted to prove that this function ball, this thin strip, which is a thin rectangle centered on 0, should absorb these functions. Remember, we're working only on the interval 0 to half. And then I said go far enough along that 2 to the minus n is less equal to epsilon, and that was fine. And once you've gone that far, your strip will absorb the functions from that point on. And then I wrote some rubbish because I missed out 2 minus signs because I was doing it too fast. And I said, how close is fn of x to 0? It's at least modulus of it's exactly modulus of x to the n. And assuming that n is, well, we know that that's less equal to 2 to the minus n. That's 1 over 2 to the n, which is 2 to the minus n. And then because n is at least as big as capital N, that's less equal to 2 to the minus capital N, which is indeed what we chose to be less equal to epsilon. So I'd been all right if I hadn't missed out those 2 minus signs, but I did also say it without the minus signs, which is more embarrassing. But anyway, that's fixed now. So there are the 2 typos, and now we'll move on from there. So here's an interesting sequence of functions. This is a bit like a sequence of functions that we just dealt with in the examples class. So I'll just show you what these ones do. Like the ones in the examples class, they start from the origin, go up in a straight line to height 1, and then, but this time, they carry on at height 1 forever. And the gradient they go up with is 1 over n. So let me say explicitly that f1 of x is x if 0 is less than or equal to x is less than or equal to 1, and 1 if x is greater than 1. f2 of x is x over 2 if 0 is smaller equal to x is smaller equal to 2, and it's 1 if x is bigger than 2, and so on. So you can just substitute in each value of n, and you'll get the definition of these functions. So now I can sketch them for you, and I've already described them. They go up to height 1 and then carry on at 1 forever. They all take values between 0 and 1. So I can sketch them on the positive real axis like this. So if 1 of x goes up like y equals x until it hits height 1, let's get my height 1 going across properly. And here's y equals f1 of x. Y equals f2 of x does the same thing, except that it doesn't get up to height 1 until you get over to 2. Yeah, 3 of x does the same thing at 3. I think I'll go under this time. You see, it's actually very difficult to do this properly because you've got to indicate all these different functions which are still going along the same line. And finally, I'll stick it left 4 of x, which gets to here, if I can. And off it goes. And they all go off forever along that straight line. But I can't bother to put all the dots in. Anyway, I've run out of room at the right. So they stay at height 1 and off they go. Well, these functions are very like some other functions I asked you to look at earlier. And you can check quite readily that they converge to 0 pointwise. Show that Fn tends to 0 pointwise. I'll give you a hint for that, though. You can use the sandwich theorem if you've already done the other one. Hint. If you want to avoid doing case-by-case analysis is also perfectly fine, but note that naught is smaller or equal to Fn of x is always less or equal to x over n, which tends to naught as n tends to infinity. So you can use the sandwich theorem. I'll let you fill in the details of that. But it doesn't converge to 0 uniformly, because if you take a little thin strip centered on 0, take a thin horizontal strip centered on 0, you get something looking like this. And let me choose a height. Let's say that's a fifth. You should choose a specific value for your bad epsilon. So that's minus a fifth, and that's a fifth. It doesn't converge uniformly because none of these functions are stuck in that grey strip. The functions always get out of that grey strip because they always manage to get up to height 1 somewhere. So none of them stay between minus a fifth and a fifth. So none of the functions Fn are in that grey strip. So this function ball, those are the functions that get stuck inside the grey strip. And we've seen that they all escape because they all manage to get up to height 1 somewhere. So that gets them well outside. Did I say a sixth? I think I was going for a fifth above. It doesn't really matter. You have to choose what epsilon you want and stick with it. None of the functions are in there. So that ball does not absorb the sequence in particular. Again, we always got these extreme examples where the ball not only doesn't absorb the sequence, but none of them are in. That's what we've been doing so far. And so the sequence does not converge uniformly to 0. Any questions about this example or in general about uniform convergence? Yes?
Why would you take a bigger epsilon instead of a phi? Take it greater than 1.
Okay, so if you took an epsilon bigger than 1, it would be absorbed. But for convergence, it has to be every ball absorbs it. So for uniform convergence, it should be all epsilon, it works. So to show it doesn't converge uniformly, you just have to find one bad epsilon. And so that's a good point. There are some epsilons that work, but for it to be uniform convergence, all of them must work, and it's the small ones that count. Because if a small one works, the bigger ones do as well. So you only really need to check really, really small epsilons. And if they work, if all of the really small ones work, then you're home. But if you find a small one that doesn't work, then you proved it isn't uniform convergence. So yet again, you only need one bad epsilon to fail uniform convergence. Any more questions about these examples or uniform convergence, pointwise convergence, before we finish off this chapter? Okay, it's pretty tricky stuff, this. It's probably harder than anything else we've done in the module. So if you can get used to all these examples of sequences of functions, you're doing really well. If you look at question sheet 5, you'll see some discussion of something called the uniform norm, which measures how far apart two functions are uniformly. And that gives you a notion of distance between two functions. And if you use that notion of distance between functions, you can get the notion of convergence using that distance. And everything becomes a slightly more, it's a slightly more standard way of looking at things to use a uniform norm. But you don't usually define uniform norm unless you're dealing with bounded functions. So my approach with the function balls is very slightly more general because you don't have to be dealing with bounded functions in the first place. But they're very closely related, as you'll see if you look at question sheet 5. So uniform convergence is much stronger than pointwise convergence. We see lots of examples of pointwise convergence where you didn't have uniform convergence. We've seen how to establish pointwise convergence. In at least one example, we did it in full. We've seen how to establish uniform convergence. It's a bit harder, but we did see one example of that. And we see lots of ways to show that things don't converge uniformly by finding one bad epsilon. Now, why is uniform convergence so much better than pointwise convergence? Because pointwise limits of continuous functions may be discontinuous. We saw examples of that. That first example we looked at, we had a sequence of continuous functions and they converged to a discontinuous function. The functions x to the n defined on the closed interval 0, 1. They're really nice and continuous, but the limit function had this funny jump when you got to 1. But uniform limits of continuous functions are always continuous. But we don't have time to prove it. I usually prove this in my 4th year module on functional analysis. Sometimes it gets proved in the 3rd year module on metric and topological spaces. But basically it says a uniform limit of continuous functions is continuous. So if you do have continuous functions and they converge to something uniformly, the limit must be continuous as well. You're allowed to state that result now. You're allowed to state it because I've told you it, even though we haven't had time to prove it. And the nice thing about me letting you quote that is that you could go back to that first example where some continuous functions tended pointwise to something that was discontinuous, and you don't actually have to bother with drawing the grey rectangle anymore because you can say, well, the limit is discontinuous and the functions are continuous. They can't possibly converge uniformly to a discontinuous limit. So you already know that they're not converging uniformly for that reason. But of course, we haven't proved that theorem. but you're allowed to quote it as a standard theorem. And if you want to see a proof, you can find it in the book of Wade. So uniform limits are very good. But other things can happen as well. Point-wise limits can be very bad in other ways. A sequence of bounded functions can converge to an unbounded function point-wise, and a sequence of unbounded functions can converge to a bounded function point-wise. I'll leave you to think of some examples. Doesn't happen for uniform limits. Let me not bother with all that stuff. I've already said that, basically. So let's move on to some final facts about uniform convergence. So proposition 9.1.7, the idea of this is to show that a sequence of unbounded functions cannot converge uniformly to a bounded function. But the first part of this is to note that if you've got a bounded function and you look at some function ball and you've got another function in that function ball centered on a bounded function, then they're bounded as well. And although I'm not going to prove that, I will give you a little sketch of it. So I'll draw a little sketch of that thing in a moment. Once you know that, you get the second one for free, because if everything in the function ball is bounded, then none of the unbounded ones can get in there. So if all functions in the epsilon function ball are bounded functions, then none of these approximating unbounded functions could be in that function ball, or else they'd be bounded functions. So if you can prove one, you get two for free. So all you need to know is that if you're in some function ball centered on a bounded function, you're still bounded. And then, as I say, what you get is it's impossible for things of unbounded real-valued functions to converge uniformly on your domain to a bounded one. And it's the same the other way around. It's impossible for a sequence of bounded ones to converge uniformly to an unbounded one. Point-wise convergence is another matter. You can find examples for yourself of sequence of functions that do all sorts of strange things point-wise. So the key to all this then, is that you suppose you've got a bounded function. If f from D to R is bounded, then say minus m is less than or equal to f of x is less than or equal to m for all x in D. And then if G is in that little epsilon ball centered on F, then the smallest G can be is minus m minus epsilon, and the biggest G could be is plus m plus epsilon. So that's G of x for all x in D. And of course you could draw a little sketch of that. So if this is y equals f of x, I don't like that one. I'm going to draw a slightly different one, sorry. Then I'll draw the function ball. Come back. Too far over again, sorry. And then if G is somewhere between those two, which is what you need to be in the function ball, well, you can see G is stuck between f of x minus epsilon and f of x plus epsilon. F is bounded, so G is almost as bounded as f is. It might get a tiny bit bigger, it might get a tiny bit smaller, but if f is bounded, so is G. And you can use the same reasoning to show that if f is unbounded, so is G. And that's how it works. Any questions about that before we move on to the next chapter? If not, I'll give you a 2-minute break, a chance to pick up any handouts if you haven't got them.